All right, hello and welcome everybody to our talk, Dissecting QNX, Analyzing and Breaking Exploit Mitigations and PRNGs on QNX 6 and 7. My name is Wetzels, and I'm currently an independent security researcher with Midnight Blue, where I mainly focus on embedded systems security. I previously worked as a security researcher at the University of Twente in the Netherlands, where I focused on critical infrastructure protection, and most of this work was done as part of my master's thesis at the Eindhoven University of Technology in the Netherlands.
And my name is Abbasi, and I'm a PhD student at Eindhoven University of Technology and visiting researcher at the Chair of System Security of Ruhr University Bochum in Germany. My research mostly is about embedded systems, binary security, and industrial control systems.
All right, so I'm going to start this presentation off with an introduction to QNX, discussing a little bit about the operating system and security architecture, then moving on to the pseudo-random number generators, the exploit mitigations, and finishing off with some final remarks. So what is QNX? QNX is a Unix-like POSIX-compliant real-time operating system. It was initially released in 1982 and later acquired by BlackBerry. It's closed source and proprietary, so all of this was obtained by reverse engineering. There's two main lines of QNX right now. There's QNX 6, where the latest version is QNX 6.6, and that's a 32-bit operating system. And then there's QNX 7, which was released in March of 2017, and that's a 64-bit operating system. It's most famously known for its use in mobile systems. It forms the basis of BlackBerry 10 operating system, as well as the BlackBerry tablet operating system. But that's really only the tip of the iceberg of QNX usage. Because these days, it's obviously far more prominent in automotive. It holds more than 50% market share in infotainment units, for example, and is set to be used in various self-driving car initiatives, such as the one by Delphi Automotive, which has partnered with BlackBerry on this kind of project. Another interesting application is the usage of QNX in Cisco iOS XR, which is the operating system used in carrier-grade routers by Cisco. As you can see on the right of the slide, QNX forms the basis of this operating system. And that makes for an interesting target as well. And outside of that, it's used in many, many more critical systems you see everywhere around you. Industrial control systems, including the nuclear power plants by Westinghouse, turbine controllers, defense applications like UAVs and military radios, medical applications, railway safety, you name it. There's enough reason to be interested in QNX security. So some of you might remember that not last CCC, but the CCC before that, we talked a little bit about the PRNGs of QNX 6.6. But in this talk, we'll talk about the new PRNGs they introduced in QNX 7 in user space and kernel space, mostly as a result of our research into QNX 6. And we'll talk about the exploit mitigations of QNX 6 and 7, which have not been discussed before. So let's start with the operating system and security architecture. Ali?
Yep, thanks. So QNX basically is a true microkernel, and what it means that basically most of the functionalities which usually you find in monolithic kernels are outside of the kernel. And the reason, well, partially it makes the operating system much more stable, and of course there will be less ropes for offensive guys like you to hang on them. So how putting lots of these components of the operating system outside of the kernel like scale. So basically the core or the heart of the QNX basically is its message passing functionality, which means that these device drivers and lots of protocol stacks residing in user space, and then they communicate with a client-server architecture, which we call here like message passing, and communicate with each other and with the microkernel. And microkernel basically is like really, really tiny, like scheduler, like very, very basic, essential stuff there. We can divide generally the attack surface in QNX to two parts. So either a local attack surface and a remote attack surface. So there are lots of things in local attack surface or process manager, like resource manager, lots of things like that, which attacker can target, and also the microkernel itself. And then in the remote part, you have network managers, like network services and all of them, which can get targeted, which I talk about them in one example later. But here is important thing. Because lots of these essential services, so for example, a device driver might run with a root user, there's really, maybe there is no motivation for attackers sometimes to even target the microkernel, because targeting the microkernel itself is the hardest part. So sometimes the attacker even don't need to target the microkernel because the device driver already have lots of access to lots of things. So looking back at the security research history in QNX, so from 2011 to 2014, BlackBerry Mobile Research did lots of work on it. Mostly not about like directly QNX, but about the BlackBerry Mobile OS, which its kernel is basically QNX. And there was one very interesting talk in 2016 by Alex Plaskett on QNX inter-process communication and kernel calls, which I recommend you. It's in YouTube to watch it. There were various other individual vulnerabilities, such as work by Julio Cesar Fort. Yeah, so overall, if we make observation of all of these reported vulnerabilities, we can say most of them are about setuid logic bugs, some memory corruption vulnerabilities, and lots of insecure permission problems, basically. One interesting one was last year by the WikiLeaks leak named Vault 7, which was showing that United States Central Intelligence Agency are interested in targeting QNX in their embedded development branch, which they didn't do until almost end of 2014, but we don't know after that, maybe they did. So overall, there was no prior work on exploit mitigation and pseudo-random number generator of QNX, and almost no work on its internal designs. So let us start with the syscalls. So QNX support around 90, so in some versions maybe 99, but overall let's say 90 like syscalls, and they also like compared with Linux, which we have over 300, it's much less, but also they implement like lots of POSIX syscalls, or like basically like libc functions as a message passing stops in their implementation. So the syscalls invoke with typical instruction also, like so sysinter, int0x28, svc or swi in ARM, and the syscall number get located in EAX, in R12 in ARM, and in PowerPC R0, and the listing are located in kernel calls.h file. So upon the entry to the like basically when you make a syscall, you enter to the kernel in a kernel entry or kernel sysenter, and basically what will happen is that you are saving the registers and then switching to the kernel stack and get the active trait, wait for the right CPU, and then acquire the kernel. Interesting thing is that so basically they are using a syscall number in an index into a kernel call table, and in older QNX, for example, you could make a number which doesn't exist as a syscall number, so a higher number, and then just jump to some other part of the kernel because you are overpassing that table. So booting process in QNX. So once the hardware initializes, what you will have is that you have an initial program loader which copies basically image file system to the RAM, and then you have startup program which configure the, for example, interrupt controllers, and then after that you basically load the microkernel or proc NTO, which we talk about it again later, and basically so it set up the kernel and run build files, and later you eventually, depending on the application, because it's an embedded operating system, you load, for example, HMI if it's a car entertainment or whatever. So again, QNX is an embedded operating system. So basically it means that it will be used in different applications. So it can be used in space-borne applications, or in automotive industry, or medical devices. But the point here is that most of those QNX neutrino core binaries will remain the same there. And it comes with 3 different flavors with the images. So either it is IFS, which we talked before, or flash file system image, or embedded transaction file system. And they can be combined into a single image in a, for example, NAND flash. Dumping the IFS or EFS is also very simple because actually QNX provide you a functionality, like a tool to actually do that. So as you can see in this example, we are just dumping the EFS or IFS in English in QNX. So next is a memory layout. So you will have kernel space and user space separation supported by QNX. And the only thing which is running in the in the kernel space is basically the microkernel, the proc NTO, which we talked about before. Not the whole of proc NTO, just part of it. The other part stay in user space. There's also user space separation because you have lots of sensitive application running like within the user space, so device drivers, protocol stacks. So there will be support for virtual private memory in user space application via memory management units. And also you will have lots of Unix-like process access control, which I talk about later. With respect to user management, so you have all of those standard stuff which you find in Linux, so sudo or logging, and also lots of this file permission models, and so you have also etc. password, etc. shadow, and QNX also support mandatory access control list, like similar to Linux. We respect the hashing mechanism with the passwords. So by default, it supports SHA-512 in QNX 6 and SHA-256. However, it also do a backward compatibility, so it supports also MD5, which is, I don't know, I don't think it's a good practice, considering that in these embedded devices, once you have a password, and this password something like based on MD5 can get cracked, so there will be a long life shelf for those passwords. So, but still, it's there. And in QNX 7 and QNX 6.6, the patched ones, basically they only support PBDK DF2, SHA-512 or SHA-256. Default one is 512. So the process manager in QNX is basically combined in the proc NTO, which I said before. The proc NTO basically run as PID1 and invokes basically the microkernel the same way as other processes. But it have a ring 0 syscall privilege basically. As said again before, it also supports standard POSIX stuff. The file format of the binaries are ELF, and if, for example, file system is memory mapped, the code can be executed in place. So, process abilities. And basically, QNX provide something, I guess everybody knows, rootless execution. And also, for example, you can obtain certain capabilities before dropping the root or restricting certain actions even for root user. And the abilities which QNX provide is like based on domain, range, or inheritance. And you can basically specify custom abilities. However, it's really depending on the system integrator to implement these things correctly, and lots of developers in embedded development environment usually don't know how these abilities, what kind of functionalities they further provide, and so some uncovered functionality exists there, for example, in file system or network, which the developer might not know. Of course, in security community, it's very well known, but it might not be known in embedded development environments. So therefore, lots of these capabilities can be used to elevate to root, or even maybe you don't need root because you can get access to certain things, which we show later. So there is no really true sandbox there in QNX, while a developer might trust it as it is. So here's an example of rootless execution basically in QNX. So a lower child process with certain abilities can install interrupt service routing handler, which runs in the kernel space. And basically here we are invoking arbitrary code within, which is located within the microkernel. And interesting thing, one of the interesting functionalities within the QNX is basically this QNet. So QNets make it possible for multiple microkernels communicate with each other over the message passing functionalities which we discussed before, either over the serial communication or even the network, so over anything basically. And so it's very useful for certain applications. So for example, if you have multiple engine control unit or electronic control unit in a car, they can all share one cellular modem with each other, or an edge router can share multiple network interfaces. And as you can see here, it's mapped in a /net directory in QNX, and you can see all connected nodes in the QNet, basically in the /net directory of QNX. However, when they were designing QNets, they didn't have attackers in mind, or like they were assuming that it will be executed or being run in a trusted environment. So therefore, there is no authentication basically, and the only thing which basically you need really is that you just pass a user ID, and that's it basically. So and one QNet node basically access to all other QNet nodes in the network. Also, there is no packet integrity, which means that you can also forge your user ID. However, it's not like this. Again, you guys can hang on the existing ropes provided by QNet, because QNet, what they do is that they can limit certain user ID or map a user ID to more limited user ID. So let's say you have user ID root in, or you're claiming that you are UID 0. They can map it to UID 99 in target like QNet node. So basically limiting you from having root access suddenly in the device, right? Which sounds good, but it's not working, because basically their resource manager in QNet basically doesn't check the privilege of the user ID basically. So basically you can access to any file in the operating system and read it. Yeah, so it doesn't basically working. So basically bypass this kind of mitigation provided by QNX for any map route, which you can limit the user ID, a specific high privilege user ID to a limited one. The patch are already available by QNX for QNet, but overall QNet fundamentally is broken. Also, QNX provides lots of debugging functionalities. So for example, pdebug, which is a process level debugging, which basically like similar to GDB or like fork of GDB. And it can provide debugging functionality both over serial or TCP/IP. There's a wrapper around it, QCon, and you can remote ID connectivity over port 8000 to connect with it. There is no authentication, so you can basically upload and download files and run anything as root. And also there is a Metasploit module for it. I don't know if you guys are familiar with VxWorks, another real-time operating system in embedded world. It's something like the exploits or Metasploit module, which existed for VxWorks WDB agent by HD Moore. So yeah, there are similar functionalities existing in QNX as well. There's also a possibility to dump a running process, or even basically produce a post-crash core dumps and get it out of the device. And it's really nice if you are planning to integrate it to fuzzing or fuzzing frameworks. There is also kernel debugging functionality, or KDebug. It's only will be provided over serial only. And basically you need to recompile the source, the operating system, because you have to make the proc-NTO, which is the process manager within the microkernel, debuggable, basically. So QNX also provide lots of debugging outputs in this kernel debugging functionality, or KDebug they have. So where the error occurred, the stack content, register values, lots of information are there. Kernel code, kernel state, so all of them are provided. Yes?
Right. Thanks for that. So let's talk a little bit about the pseudo-random number generators. So this is quite self-evident, but why look at the PRNGs of QNX? Well, because they form, like on any Unix-like operating system, the foundation of the wider cryptographic ecosystem. Just use dev-random for cryptographically secure numbers is received wisdom. And the strength of exploit mitigations in some cases like ASLR or stack canaries should depend, but they don't, but it should depend on the strength of the PRNGs partially. So if I can predict a canary or an ASLR address, then it makes exploit development a lot easier. So QNX has a user space PRNG, which is accessed through the dev-random interface. It's handled by a user space service. It's a microkernel operating system, which is running as root. This is started after boot by the etc. startup script. And on the kernel side of things, as of QNX 7, they now have a PRNG as well, which is implemented in the microkernel executable as a function named random value. And this cannot be accessed directly in user space, and we'll discuss the details a little bit later. So the PRNG for the user space part for QNX 6 was covered in our talk Wheel of Fortune at 33C3, so I'll keep it short here. The underlying PRNG is based on Yarrow by Bruce Schneier and others. And there were various problems here because it was based on an older version of Yarrow instead of the reference version, and then they added a bunch of really cryptographically sketchy design decisions on top of that. But the biggest problem was that it had low quality boot time entropy. As you can see on the top right of the slide, it used clock time, clock cycles, the currently running process IDs at boot time, which is always static, and the device names, which is static as well. And then they pulled it through SHA-1, and that was basically the PRNG internal state. Now, this was very low boot time entropy quality, but to make it worse, the reseed control was broken. So during runtime, they would collect additional entropy, but they would never actually feed it back into the PRNG state again. So the only PRNG entropy that was in the system at all was whatever they collected at boot, and that was kind of bad. So after we reported some of this stuff to BlackBerry, they redesigned the user space PRNG based on our feedback. They now use the Heimdall Fortuna implementation, for those of you familiar with it. They have a couple of new entropy sources. They have a new reseed control mechanism. The overall quality seems to be much better than QNX 6, but there is some potential for weaknesses depending on system integration conditions, because obviously, usually when this is used in an embedded system, there is layers and layers and layers of OEMs with all very specific embedded requirements when integrating QNX into their product. So this is what it looks like right now in QNX 7, and in green you can see the new entropy sources. So on the top left you have a seed file, and this was integrated to basically mitigate low boot time entropy conditions. So what they have is you can supply as part of the firmware, you can supply a little bit of a file with entropy, and after the system shuts down, it will put some output from the PRNG back into the file so that the next time they boot, they have some additional boot time entropy. The second new source is the user-supplied source, which is basically via the dev-random interface, which is made writable. By default, it's world writable, which is not that good an idea, but it can be locked down with some additional permissions. And here, system integrators can write their own entropy gathering daemon to feed from whatever source is available on their embedded system. And the final source is the reseed source, which unfortunately does not contribute very high quality runtime entropy because it uses the currently running process ID, which is always static for the random service, the current time, and the clock cycles value, which are both very low quality entropy sources. This is mitigated somewhat by the fact that they also use RC4 fed with the output of the PRNG itself. So overall, it's better, but if you're evaluating a QNX system, make sure to look at what particular selection of entropy sources they chose and where they're feeding them from, but because it could be worse than you think it is. So as of QNX 7, they've also introduced a new kernel PRNG after our assessment, and this is currently only used for ASLR, stack canaries, and a couple of other security-related functionality. And you can see it pictured on the right of the slide. So what happens is they gather sources of entropy from a couple of different sources. So they have like the currently active process ID, they have the clock cycles value, they have the current time in nanoseconds, they have a random seed value which can be supplied by means of a system call they introduced specifically for this purpose. It's a system call you can only call if you have the right capabilities, by the way. And then they concatenate all of this into a single block that's fed through SHA-256. And then the output of that is chopped into individual 32-bit blocks, the first of which is kept secret. It's never actually output. It's kept as a salt value. And subsequent values, whenever the random value function is called, get output by the function. So you get a sequence of 32-bit blocks, and once the entire PRNG output state is exhausted, the entire process starts again, but this time including the seed value that was kept secret. So this is actually a quite good kernel PRNG. Let's talk about the exploit mitigations of QNX. So why look at the exploit mitigations? Well, because the mitigations that we're currently used to in the general purpose world, Windows, Linux, BSD, they didn't come falling from the sky, and they didn't have the quality they have now when they first started being implemented and being rolled out. There's actually a long history, all of you will be very familiar with, of weaknesses and bypasses and subsequent improvements that took years and years. But because nobody has actually looked at the mitigations in QNX, this similar history is not there. So there's a lot of low-hanging fruit to pick off. And there's a second point that QNX does not come from the same architectural legacy as Windows, Linux, or BSD. So they could not easily port one-to-one any improvements that were being rolled out there. So there's a lot of homebrew stuff in there. So what mitigations are available for QNX right now? Well, there is data execution prevention, there is address space layered randomization, there are stack canaries, and there is relocation read-only, RELRO, very hard to pronounce. These are not enabled by default, however, so it might just be that if you encounter a QNX firmware image, even if it's the latest version, QNX 7, whatever, then if system integrators did not explicitly enable these mitigations, it might still be exploiting like it's the 90s. So also don't expect any more modern mitigations like vtable protection. It's not there. There's no control flow integrity of any kind. There's no kernel data and code isolation. This is maybe part of the future, but as far as I gather, there's no clear roadmap for this yet. So it's just these mitigations. Now QNX has support for hardware-based data execution prevention by means of using the well-known NX and XN bits. It has support for this on x86. It also has support for this on ARM. It does not, however, have support for this on MIPS, even though MIPS 32 after release 3, I think, has support for a bit like that. For PowerPC, there's a lot of variation, but that's, you know, PowerPC. So the real problem with QNX DP is that it has insecure default settings. So regardless of whether it's enabled or not, the stack is always left executable, even though the heap is not. And if you link and compile with all the proper settings, then the GNU stack elf program header is completely ignored by the program loader. So regardless of your toolchain being set up, regardless of, you know, having hardware support for this, the stack will be executable. Now, it's possible to turn this off by specifying a particular option in the microkernel startup flags. But the problem is that this is a system-wide setting, so there's no opt-out. If you have any legacy applications that for whatever reason need to have like an executable stack, it be, you know, trampolines on the stack or whatever, then they can no longer function. And system integrators might decide, you know, they want to keep a particular application that needs this functionality and not enable this, or they're simply not aware of this flag at all. So this issue is still present on QNX 6 and 7, and it's not going away. They're not moving to any opt-out model here. So if you encounter a QNX firmware image, just check if this is among the startup flags, because if it's not, you won't have to bother with a lot of other stuff. So QNX ASLR. QNX ASLR is enabled again by starting the microkernel with a dedicated flag. Child processes inherit their parents' ASLR settings, so they can be toggled on a per process basis. They randomize the objects at a base address level, so it's not very fine-grained, but as fine-grained as most ASLR implementations. And it randomizes all the memory objects, as you can see on the right of the slide, except for the kernel code image. How terrible that is depends on your opinion of KASLR's usefulness in general, especially in embedded systems, but so far they randomize most of the stuff. A problem is that they have, in the toolchain, they have pi disabled by default. So that means that none of the system binaries you encounter by default and none of the stuff that will be compiled and linked with default toolchain settings will have position-independent executables. So any of the executable image code addresses won't be randomized by ASLR. And that kind of defeats a lot of the point there. So make sure to check whether this is enabled if you're a defender or an attacker. So in order to figure out how QNX ASLR works under the hood, I reverse engineered the memory manager. And here you can see like roughly the layout. But what it all comes down to is that under the hood it all comes down to the mmap call, which is implemented in the microkernel memory manager syscalls. And the randomization happens in the two functions that are highlighted in blue, and that's stack randomize and map find virtual address. And both of these functions, which apply the randomization in question, rely on the same random number generator, which we'll discuss in just a minute. Now the first of these functions, mapfindVA, randomizes, among other things, the virtual addresses returned by mmap calls. So the way this happens, as you can see on the right of the slide, it subtracts or adds a random value to or from the found virtual address. And it does this by taking the lower 32 bits of the random number generator result, bitwise left shifting them by 12, then extracting the lower 24 bits and applying that. And the problem is that this bit masking, regardless of the quality of the RNG, contributes at most 12 bits of entropy, which is worse in practice, as we'll see. Now the second of these randomization functions is called very conveniently stack randomize, and it randomizes the stack start address. So whenever a process is started up or a new thread is started up, this gets applied when the stack gets allocated. It subtracts a random value in the very same fashion from the original stack pointer by taking the lower 32 bits of the random number generator result and bitwise left shifting them by 4 and at most extracting the lower 11 bits. And this contributes, again, at most 7 bits of entropy, being worse in practice. This is mitigated a little bit by the fact that it's combined with the result of the previous mapfindVA function, but this doesn't matter a lot in practice. Why? Because QNX 6 ASLR has a very weak random number generator. So these upper bounds are actually optimistic because QNX 6 ASLR relies fully on the clock cycle system call. And the clock cycle system call, as the name says, retrieves a 64-bit free-running cycle counter, and the implementation of this is architecture specific, as you can see on the right of the slide. So for x86 it will simply be a call to a read timestamp counter. For ARM it's some emulation stuff implemented in the microkernel. For MIPS it's the counter register, etc., etc., etc. We evaluated the actual entropy of QNX 6 ASLR addresses. So we measured various processes across various boot sessions and then harvested addresses for all the different memory objects that are interesting. And we used the NIST entropy source testing tool to obtain a min entropy estimate. And for clarification, 256 bits of uniformly random data should correspond to 256 bits of min entropy. And we found the average min entropy of an ASLR randomized address to be 4.47 bits. So that's very weak if you compare it, for example, on the right of the slide, to mainline Linux ASLR on a 32-bit system, or the PAX ASLR patches, which oscillate somewhere between 6 and 27, 28 bits of min entropy. So why is this an issue? Well, because of the potential for QNX ASLR brute forcing. Like many Unix-like systems, QNX has memory layout inheritance. So if you have a parent process and you have, for example, let's say a forking networking daemon, where every incoming client connection is handled by a new child, then it will fork and it will make a copy of the memory layout for the child. And that means because that happens after ASLR is applied, that the ASLR layout will be the same in the child as in the parent. And for each subsequent child, it will be the same as well. And that means that if you have very low entropy, then an attacker can guess these addresses and work through the crashes and see if the child is still alive, and then get within a reasonable amount of time their payload to be active. Now, does this work in practice? Yes, it actually works in practice and quite fast. On the left of the slide you can see a vulnerable demonstration service running on port 1337, and on the right you can see a script brute forcing the ASLR, and within a couple of seconds it pops a root shell. So, this basically means that ASLR remotely doesn't really pose any kind of obstacle in QNX 6. Of course, it's nice to bypass it by brute forcing, but the main point of ASLR is not so much the randomization of these addresses as well as guaranteeing memory layout secrecy. So if you have information leaks, whether they can be exploited remotely or locally, that's always nice to have. And QNX is quite full of them, and a lot of them feel like they're from the early 2000s, and we'll highlight two of them. The first of which resides in the process file system. So QNX, like most Unix-like operating systems, has support for a process virtual file system, and here every process has an entry, and you can do some information querying about the currently running processes by using the devctl API. Now, as you can already see in the slide, the good thing about this is that all of these entries regardless of the process permissions, are world readable. And what you can use for this is you can actually query these entries and get full memory mappings. You can get the program state to the registers. You can even get stack frame backtraces, and all of this information regardless of privilege boundaries. And what's very nice, as you can see on the right of the slide, is that even if you can, compile your own utility to do this for you locally, then QNX nicely provides for you a utility that's included standardly called PIDN, and it allows you to retrieve all of this information for you. So, that's a very nice local information leak. Second information leak we'll discuss resides in the LD-debug environment variable. So the LD-debug environment variable allows you to query some debugging information about an application that started. And this is particularly interesting for setuid binaries. And as we discussed, QNX had a lot of issues with setuid binaries in the past. And the problem here is that if you specify LD-debug as all and then start your setuid binary, then it doesn't check any of the permissions, the differences between the setuid binary and the current user that you are, and it simply dumps all the information for the loaded libraries. So that's a very nice second information leak. And these are just two examples, because if you just spend, a week of hunting, you'll find much more issues like these. Now, we reported these issues, and as of QNX 7, they made some changes. ASLR is still disabled by default, so the default settings are still not having ASLR enabled. There's no KASLR, but they do use a kernel PRNG now that we previously discussed, so that's theoretically much stronger. The problem is that despite the use of this new RNG and having a 64-bit address space, these low theoretical upper bounds remain because they forgot to remove the bit masking applications. So at most there's still 7 bits and 12 bits of entropy there. And I talked to the people at BlackBerry and they said, yeah, we're going to remove that, but that's going to be another patch. So that's coming. Another interesting observation, I'm not sure if they're going to do something about that either, is the fact that they always load code images in the lower 32 bits of the address space. So, that's something you kind of want to avoid as well, but I'm not sure if that's going to be patched. So they fixed the LD-debug issue, that's good, but they did not completely fix the process file system information leak. So as you can see on the top right, that's a very recent release of QNX 7, and they restricted the PIDN utility, so you can no longer query information about higher privileged processes. But if you write your own small C file, compile it, and drop it on the system, you can still query this information. So they restricted the wrong thing there. And as far as I know, this is still out there, so might be going to be patched, might be not. Didn't hear anything about that. So on to the QNX stack canaries. So QNX uses GCC's stack smashing protector, so that's what you're all very familiar with probably, and the compiler side is okay, and it's what we're used to. Now, the problem starts on the operating system side of things because the implementations there are, again, homebrew. The user space master canary is generated at program startup when libc is loaded, but unlike the regular implementation like on Linux, it does not use libssP's guard setup function for this. Instead, it uses a custom function called init cookies. And what does init cookies do, and what's the problem here? Well, the problem again is that it draws entropy from very weak sources. In this case, 3 sources, only 2 of which are relevant if ASLR is enabled. As you can see on the bottom of the slide, it uses read timestamp counter, it uses the address of a local stack variable, and it uses the address of the function itself. And the last 2 are not randomized at all if ASLR is not enabled, and if it was enabled, then it's still based only on clock cycles. So we also evaluated the canary min entropy across 3 configurations, without ASLR, with ASLR, but without position independent executable enabled, and with both enabled. And we found that the average min entropy for these canary values was 7.79 bits, and ASLR had no noticeable influence here. So it's less than ideal, because using a secure random number generator, you should have at least 24 bits of min entropy if they use a terminating style canary for a 32-bit value with a null value in the middle. So this is not the worst thing, because in kernel space the problems are even worse. The microkernel obviously is neither loaded nor linked against libc, but master canary generation is done by the init cookies function. So they would have to find something else, but QNX forgot to implement a replacement master canary routine. So the kernel space canaries are used everywhere across the microkernel, but they're never actually generated, so they're always 0, and that's not very good for stack canaries. Now, they made changes to this, and they're enabled by default now in the toolchain, and they generate, at least on QNX 7, 64-bit canaries. Based on our recommendations for user space, QNX now mixes in the ELF auxiliary vector value 80 random. And what this basically does is when it is started up, it transfers some value from kernel space to user space. And in kernel space, this value is basically 64 bits generated by the kernel PRNG. For the kernel space canaries, they now concatenate to 32-bit kernel PRNG values, so canaries are more or less fixed on QNX here. And that brings us to the final mitigation, relocation read-only. The problem what relocation read-only seeks to address is that dynamically linked binaries use relocation to do runtime lookup of symbols in shared libraries. As you can see on the right of the slide, if you call a function that's in an external library, you call a function located in the PLT, and that resolves it usually during runtime. Now this is a popular target for attacking, because if you overwrite one of these entries, then once the function gets called, the relocation data that's overridden allows you to hijack control flow. And this is where rel-row comes in. And at first you had partial rel-row, which basically works by reordering the ELF sections so that the internal data sections, like the global offset table, the destructor section, precede the program data, like the data section and the BSS section. And then the relocation data is made read-only by covering them with a dedicated segment after relocation is done. The problem is that many applications use lazy binding, so they don't resolve all of them at runtime because that would slow down startup times, but they resolve them whenever they're hit. So that means that if you do that, you cannot make it read-only right away. You cannot cover the PLT GOT segment section there. So that's left writable in partial rel-row. Now in order to address that, you disable lazy binding by using the bind now flag, and then you basically resolve all of the symbols at startup time, and you make all of the relevant internal data sections read-only. Now, QNX implemented this, but the problem is that their implementation was broken. On the left, you can see the implementation on Debian Linux, and here you can see that the GNU rel-row segment covers all of the relevant internal data sections, including the global offset table. On the right, you can see the QNX 6.6 implementation, where they forgot to reorder the internal data sections. So the global offset table does not precede the program data sections, and that means that it's the only thing that falls outside of the range of the GNU rel-row segment. And that means that even if you have all your linker and compiler settings set up according to whatever kind of standard you have, then it's still exploited, then you can still overwrite relocation data here. So it's completely useless. You can see here basically what this looks like in practice. On the left you have an application on Debian Linux. If you try to write the relocation data with rel-row enabled, you can't. On the right you have it on QNX, and you can. So that's not what you want to be the case. We also found a very weird local bypass. So the same LD-debug environment variable has an undocumented option called imposter. And the only thing it does is disabling relrow without any kind of privilege checks. I'm not sure why it's there, but it's very nice for exploiting setuid binaries. Both issues now are fixed with patches for QNX 6.6 and QNX 7, however, so these are no longer an issue. And that brings us to the final remarks. So we disclosed all of these issues that we discussed to BlackBerry. Most of the issues were fixed in 7.0. Patches are available for 6.6. But what's really important to remember here is because QNX is an embedded operating system, it will take lots of time before these patches filter down to the OEMs and eventually the end users. Especially if you have the more deeply embedded systems and the kind of systems which have very, very short and irregular maintenance windows, then when are you going to update the firmware? When are people going to contact, or reach out to their OEM and integrate the new updates? So many of these issues, even though patches are available and QNX 7 has some of these issues fixed, will be out there in the wild for a long time to come. As a conclusion, things were mostly okay on the toolchain side, but that's because they use GCC as their compiler toolchain. There were some weak defaults, some blinker mistakes, but that was not the real issue. The real issue was that problems reside on the operating system side of things. And that's mainly not because QNX doesn't know what it's doing, it's because QNX cannot benefit directly from any work that's been done in general purpose operating system security. Because it cannot easily port whatever is being done in Linux, being done in Windows, being done in BSD one-to-one. They have a very different architectural model. And the result is homebrew DIY mitigations which are very subpar. What's also very evident is that there has been a complete lack of prior attention by security researchers. A lot of the vulnerabilities feel like they're from the early 2000s. And of course, embedded random number generator design remains difficult. Entropy issues mean that the design burden rests with the system integrators because you cannot account for entropy sources if you don't know what kind of entropy sources will be available across the hundreds of thousands of different configurations that your OS will be deployed among. On a more positive note, at least QNX attempts to keep up with general purpose operating system security. I looked at a lot of other embedded operating systems, as I discussed in my talk, the RTOS exploit mitigation blues at 2017's hardware.io conference. And they're one of the very few non-Linux, BSD or Windows-based embedded operating systems that actually bothers to implement mitigations. They had a quick and extensive vendor response, and they had a good integration of the feedback we gave. But there really is needed more attention to embedded operating system security in general. You can expect more QNX stuff in the future. I should, of course, have removed OffensiveCon here. But we're going to cover some additional issues at Black Hat Asia and Infiltrate. So if there's any questions, I'll take them now.
You said that the RNG loads RNG state on boot and then saves it on shutdown. Does it also write the RNG seed file on boot in case the system crashes? Or is the system, if it crashes, going to reload the same seed on second boot?
No, it only writes it like when it shuts down, and it reads it during boot. Like if the system crashes or in any way would be like glitched or something like that, then it uses the same seed file again.
Is BlackBerry still shipping 6.6?
As far as I know, 6.6 is not the underlying QNX version for BlackBerry 10 and BlackBerry Tablet OS. I think that is 6.4 or 6.5.
Yes, they do still ship the 6.6.
Yeah,
it's an option to, you can choose, like you can go for QNX 7 or you can go with QNX 6.6, yes. So they are still shipping it for OEMs.
So there are OEMs still releasing new products like
yes.
today with 6.6?
Yes.
Yeah,
Okay.
yeah.
Okay,
Definitely.
thanks.